Hi there, I'm Mike from Prep 101, and in this primer we'll be going over Lewis structures. These are absolutely foundational, so fundamental, and are going to be both tested directly and built upon in this course. Without any further ado, let's jump right into them. There are a few steps to drawing Lewis dot structures. We're going to go through CH4 with each of these steps. The first step is to count the total number of valence electrons. So for carbon, let's see, we find carbon on the periodic table and count its valence electrons 1, 2, 3, 4. Okay, so we have 4 plus, for the hydrogen, there are 4 hydrogens, and each hydrogen has only 1 electron. So we come out with a total of 8 electrons here. Then we make a reasonable skeleton, and I have that in quotes because that is going to be a little bit nebulous. It might get a little bit complicated, but that will be covered in your course. For now, we're focusing on the relatively easy versions. The reasonable skeleton for CH4 would have carbon in the center, and then the hydrogens all around it. Carbon is very often going to be at the center of Lewis dot structures. Then we give the outermost atoms octets. And there are 2 things to specify here. Octets means 8 electrons. But we have this little asterisk here because this is only usually true. If you have something very early on the periodic table, it's likely not to have an octet. Things that are before boron often don't have octets. Hydrogen is the classic example for this. Hydrogen has a duet, which just means it has 2 electrons. It's worth being really clear here. Each bond has 2 electrons. Each lone pair also has 2 electrons. So these lines there, those bonds, those all have 2 electrons. Based on this, okay, the hydrogens, we see that they have 2 electrons, and they're actually happy like that. Then we look at the inside atom. This carbon, well, let's see, how many electrons does it currently have? It has 1, 2, 3, 4, but those are 4 bonds. This hydrogen has 4 bonds, and therefore it has 8 electrons. All right, let's move on and do a slightly more difficult example. Here we're looking at NH3, or ammonia. So like before, we count the total number of valence electrons. And you can pause the video and give this a go if you'd like. So we're going to count these for nitrogen. That's going to be 1, 2, 3, 4, 5. So 5 electrons from the nitrogen, plus 3 times just 1 from the hydrogen. And as a result, we find that this one also has 8 valence electrons. Our reasonable skeleton is going to have nitrogen in the center and the hydrogens on the outside. Hydrogen is never going to be the center of a Lewis dot structure. These hydrogens already have their happy duets, so they're all good. And we're supposed to give excess electrons to the center atom. Well, we've currently accounted for 6 electrons, but we have a total of 8. As a result, we're going to add 2 electrons to that center atom. We should check now. The center atom, how many electrons does it have total? Well, it has 1, 2, 3 bonds, giving it 6 electrons, and 1 lone pair, giving it 2 electrons, totaling 8 electrons, so it has achieved its octet. And therefore, it's pretty happy. Try pausing the video and give this one a go. All right, going through this one a little bit faster now. Our number of valence electrons for oxygen is going to be 6, for chlorine, 7. So we have 6 plus 2 times 7. Again, remember that 2 there. And that's going to come out to, let's see, 20 electrons. Our reasonable skeleton has oxygen in the center, and you could have put the chlorines at an angle here if you wanted to. It doesn't make a difference. Now we give the outermost atoms octets. Our outermost electrons finally are capable of having octets. So we draw all those in. Let's see where that leaves us. We have 2, 4, 6, 8, 10, 12, 14, 16. We have 16 electrons so far. We need 20. So we're going to give excess electrons to the center atom. We're going to give it 4 electrons. That's 2 lone pairs. And now this entire molecule has 20 electrons, and as a result, it is happy. That's the most basic version of drawing Lewis dot structures. There's one additional twist that you're going to need to know going into your university courses. That is how to incorporate formal charges. Steps 5 and 6 are going to be to check the formal charges and add double bonds if necessary. To calculate the formal charge, you have to consider the number of valence electrons, lone electrons, and bonds. Let's do this for ammonium, NH4+. So we have to draw the structure first. Let's try it. So for the nitrogen, that's going to have 5 valence electrons plus 4 hydrogens, each one having 1 valence electron. But wait, that's not all. We have this positive sign, which means the atom has lost 1 electron. You can imagine lithium going up to its friend and saying, it's a nightmare, I've lost my electron. And lithium's friend says, lithium, are you sure? And lithium responds, I'm positive. When you have a positive ion, that means that it has lost an electron. So, okay, we can do that math. We get 9 minus 1, we get 8 electrons. Nitrogen is going to be our central atom, as usual. And all right, so we've drawn that up. That already accounts for all 8 electrons. Let's now do this calculation. So the number of valence electrons for this nitrogen is going to be 5. That's just based on the periodic table. We found it in the exact same way as usual. The number of lone electrons here, no lone electrons. And the number of bonds is 4. So we have 5 minus 0 minus 4. So our formal charge is equal to positive 1. We're not going to get too deep into formal charges here. It's just enough to be able to calculate it based on a proposed Lewis dot structure. Let's see how this works with another example. with CH2O. We'll go through the first steps pretty quickly. For carbon, we'll have 4 valence electrons. For the hydrogen, a total of 2. For the oxygen, a total of 6. That's going to give us 12 valence electrons. Our reasonable skeleton is going to look something like this. We can give our outermost electrons octets where they need them. And now we have our first approximation. So, all right, we're giving excess electrons to the center atom. Do we have any excess electrons? Let's see, 2, 4, 6, 8, 10, 12. So we already have all 12 of our electrons accounted for. Then we're told we need to check formal charges. Well, okay. Whenever you're checking formal charges, checking the center atom is always a good place to start. So for that, our formal charge is going to be equal to the number of valence electrons on carbon from the periodic table, so that's 4, minus the number of lone pairs, that's 0, minus the number of bonds. We come out with positive 1. Let's also take a look at the formal charge of this oxygen. We've seen hydrogens like this a lot. We're probably pretty sure that hydrogen's just fine. So our formal charge for oxygen is going to be, let's see, 1, 2, 3, 4, 5, 6. Its number of lone pair electrons, so it has 6 lone pair electrons, and it has 1 bond. As a result, it is -1. So to be clear, that's +1 for the carbon and -1 for the oxygen. We want formal charges to be 0 as much as possible. So we're going to do something a little bit clever here. We're going to take some of these electrons from the oxygen and put them down into this bond. When we do that, we come out with a different structure. We come out with a double bond between the oxygen and the carbon. And now the oxygen only has 2 lone pairs. If we were to calculate these formal charges again, you'd find that both of these formal charges are now 0, which means this molecule on the right is a better Lewis dot diagram than the one on the left. We have one final example now. This is CO2. Try giving this one a go, and then we'll go through it relatively quickly. All right, let's go through this. Total number of valence electrons, we're going to have 4 plus 2 times 6, giving us 16 total electrons. Our reasonable structure has carbon at the center. We give our outermost atoms octets. And let's see how far we've gone here. We have 2, 4, 6, 8, 10, 12, 14, 16. 16 electrons accounted for, which means we've already used up all of our electrons. But when we do that formal charge calculation for carbon, we find that it's 4 minus the number of lone pairs, lone pair electrons, 0, minus the number of bonds, we find that it has a formal charge of +2. That's not very good. We want atoms to have a formal charge of 0 if possible. So let's see. If that carbon needs more electrons, it can take some electrons from the oxygens. You could do this one at a time if you wanted to. I'm thinking that since we have a formal charge of +2, we're going to need to take 2 lone pairs and put those into the center carbon. So that gives carbon a double bond to both oxygens. and we haven't changed the number of electrons, we can check our formal charge calculation now. Our formal charge is equal to 4 minus the number of lone pairs, 0, minus the number of bonds, 4. Our formal charge is now equal to 0. We can do the same thing for oxygen. Our formal charge is equal to, let's see, it's going to be 6 on the periodic table, minus the number of lone pair electrons, 4, minus the number of bonds, that's 2. It's also equal to 0. This is a happy, happy molecule. All right. I know this one was a little bit tricky, a little bit long, but congratulations for making it through. Your key points are to double check the electron total at the very end. It's so easy to make a mistake partway through. Checking at the end is super critical. Make sure to check formal charges and make double bonds when necessary. And finally, when possible, work with pencil because that's just going to save you a lot of frustration. I hope you found this video helpful. If so, check out others like it, outlining the foundations of first-year chemistry in this Primers playlist. Also, be sure to join the Facebook Study Hub group. I'll put a link in the description so you can find it easily. And finally, I hope to see you at our preparation sessions. This is where I'll be outlining how to do so many questions so you can go into your midterm and exam with confidence and earn top marks. Many of the midterm preparation sessions are actually free. That's right, free. Go to prep101.com for more details. Thank you for watching.